Written in the Rocks by Kevin, Paola, and Cindy. People have known about fossils since the time of ancient Greece, but have only been regarded as remnants of still living species or the remains of mythological creatures. People had no idea how to interpret what they were or from what animal they came from. Take a look at this elephant skull, for example. Many would believe that this skull was that of a cyclops. It is easy to interpret the bone as something that it is not when there is little to no information identifying fossils. In the 21st century, we have understanding and technology to interpret what these remains really are. Impressions of prehistoric organisms that have been preserved and that might not exist today. However, finding a fossil is not as easy as it may sound. In order to become a fossil, an organism first must die. Next, the organism's body must be covered up quickly by sediments so that the organism's body can avoid being picked at by scavengers. It is best for the organism to die near a large body of water so the current can assist in piling the sediments over the body. For this reason, most of what the fossil record is today comes from prehistoric marine life. Groundwater then passes through the skeleton, bringing an abundance of minerals. Over time, as the minerals harden, they replace the decaying skeleton, leaving an imprint in the sediments. Think of this as making a cast of the organism's bones. Finally, the fossil must wait to be discovered with the help of erosion, low water levels, and other effects that allow fossils to rise. Fossils are usually found in sedimentary rock. Sedimentary rock is usually composed of layers called strata. The oldest rocks are found at the bottom layer, and the youngest rocks are found at the top layer. This law of superposition was composed by Danish scientist Nicholas Steno. If a layer of the same type of rock is found in another area, we can conclude that both rocks are the same age. Like fossils, rocks found in strata demonstrate minimum age. To find the actual age of rocks, we use radiometric dating. Radioisotopes are embedded in igneous rock. The radioactive elements have a rate of decay that scientists have termed as a half-life. A half-life is half the time it takes for a radioisotope to decay, giving us the time required to estimate the rock's age from whatever it started to what remains. For example, uranium-235 has a half-life of 700 million years that we can use to date older fossils. Carbon-14 has a half-life of 5,700 years, and we use it to date more recent fossils like human remains.
As we look to the fossil record, we notice how incomplete it is due to the fact of how rare it is for an organism to become fossilized. That begs the question of how one organism can evolve to look like another completely different animal or plant. In order to answer this question, paleontologists look for transitional forms. Transitional forms bridge the gap between two very distinct organisms. By finding transitional forms, we understand how organisms evolve over time to become what they are today. Microevolution deals with minor changes within a species over a short period of time, while macroevolution deals with the evolution of an entirely new genus, phylum, class, and so on. In other words, macroevolution deals with the evolution of an entirely new taxonomic groups over a long period of time. For every two species, no matter how different, there was once a single species that was ancestor to them both. In some cases, that species is referred to as the missing link. Like I've mentioned earlier, the fossil record is extremely spotty, therefore it is incredibly hard to find a missing link. So what do we do? What a biologist would do is make a prediction about the missing link and what they would have expected to look like. For example, biologists in Darwin's days figured out birds were closely related to reptiles by comparing their hearts and skulls. But one thing to keep in mind is that the transitional form will not be a combination between two species, but instead have similar traits that connect the two. When looking for a transitional form, you must know where it would be on the geological timescale. So in the case of birds, reptiles evolved much earlier than birds. So if we were to look for a transitional species for birds, it must be located after reptiles had already evolved, but before we see modern birds in the fossil record. We would then look in strata that would coincide with the appropriate geological time. To explain this concept further, we will look at the transitional form between fish and amphibians. Lobe-finned fish appear 390 million years ago in the fossil record, and terrestrial tetrapods appear 360 million years ago. So if we were to look for a missing link between the two, we would expect to find them between those time periods. Niels Schubin did just that and set out to find this missing link. He knew it must have been between 390 and 360 million years old, and it must have lived around fresh water since that is where lobe-finned fish resided. He concluded that Ellesmere Island in the Canadian Arctic met all these requirements and set out to find the missing link. After 5 long years of searching, Schubin at last found his missing link, Tiktaalik rosea. This creature met all the marks of a transitional form between fish and amphibians. Tiktaalik had gills, scales, and fins. It lived most of its life in fresh water, just like a lobe-finned fish, but it also had critical traits that makes it a transitional form. It had a flattened head with eyes and nostrils on the top of its head, compared to a lobe-finned fish, which would have it on the side. Having eyes on the top of its head will allow it to peek its head out of the water to survey its surroundings. Its most defining feature is its more robust fins. In other words, Tiktaalik could basically do a push-up. Another key feature that separates Tiktaalik from a fish is its necks, because fish don't have necks. Although it sounds like all those key traits would make Tiktaalik able to live on land, that was not the case. Its limbs could be used to project its body upwards, say to help peek its head out of water, but that doesn't mean it could walk on land. In fact, Tiktaalik was unable to walk on land. But if natural selection selected for Tiktaaliks that ventured out of the water, let's say into further streams for a better food supply, then that could have led the way into the evolution of sturdier walking limbs.
Birds evolved from early reptiles, but how does a land-dwelling animal evolve the ability to fly? Intermediate changes in the evolution of flight give us this answer. There are fossils that show how flying birds evolved. Since the 19th century, the similarity between the skeletons of birds and some dinosaurs led paleontologists to theorize that they had a common ancestor. Approximately 200 million years ago, there were theropods, agile carnivorous dinosaurs that walked on 2 legs, but they were not bird-like. Approximately 70 million years ago, we see fossils of birds that look much older. We should expect to see the reptile-bird transition between 70 and 200 million years old. Perhaps the most famous of all transitional forms is the Archaeopteryx lithographica, which was discovered in a limestone quarry in Germany in 1860. Its feathers were left as imprints. It is actually more reptile than bird, its skeleton almost identical to that of some theropods and had reptilian features that include a jaw with teeth, a long bony tail, claws, separate fingers on the wing, and a neck attached to its skull from behind instead of below. Non-flying feathered dinosaur fossils date between 135 and 110 million years ago. These are Archaeopteryx cousin ancestors. As these fossils get younger, the reptilian tail shrinks, the teeth disappear, the claws fusing together, and the appearance of a large breastbone to anchor the flight muscles. These fossils show the basic skeletal plan of birds, and those essential feathers evolved before birds could fly. Bird evolution is the refashioning of old features into new ones, just as evolutionary theory predicts. Whales have an excellent fossil record. They are one of the best examples of an evolutionary transition. Hippos are the whale's closest living ancestor. They spend most of their time submerged in tropical rivers and swamps. They survey their domains with their eyes, ears, and nose, which sit atop their heads, all of which can be tightly closed. They mate underwater. Their babies can swim before they can walk and suckle underwater. They are prone to sunburn, so graze at night, and secrete oil that acts as a sunscreen because they sunburn easily. Whales can produce live young that they feed milk. are warm-blooded and have hair around their blowhole. They have vestigial traits like a rudimentary pelvis and hind legs that show that their ancestors lived on land. We can trace these traits from a terrestrial to an aquatic form, except for the tail, which does not fossilize. We can track the evolution of the whale from the raccoon-like mammal, the Indoheus, a cousin ancestor to the whale. There are hundreds of other examples of evolution at work, horse and human fossil records, just to name two. An insect example would be the ant. A transitional state between an ant and a wasp was found by E. O. Wilson and his colleagues in 1967, with wasp-like and ant-like features. A 530-million-year-old fossil found in China, resembling a small eel with a frilly dorsal fin, had a head, a brain, heart, and a cartilaginous bar along the back, the notochord. Perhaps it has roots in our own evolution. The fossil record teaches us three things. 1. Evolution happened, and it shows us how. 2. When transitional fossils are found, they are exactly where they should be in the fossil record. 3. Evolutionary change, even when major, is always building upon prior characteristics. There is no optimal design. Natural selection only acts on what exists.